time doing a lot of deep learning and neural network work for work over the past couple of months, and man, there's a lot of relatively low quality information out there. There are a lot of people that just want to explain backpropagation and write about derivatives and matrix multiplies and all that stuff, and that's cool. But if you're like me, you're just trying to figure out, can I even make this work? What am I trying to do? I figured I'd make something for you guys, and just this will include my observations about actually classifying images. So I thought I would choose a stupid topic. We're not doing dogs and cats. We're doing, is it Bill Gates or is it Jeff Bezos? So with machine learning, if you want to predict whether or not an image is Bill Gates or Jeff Bezos, you need images. Now, a lot of times you might hear people saying you need, a huge GPU, a graphical processing unit, you need to use cloud computers. And yeah, if you're trying to win the Imagenet competition, which is like 1,000 categories or something and millions of images, sure, you need real computers. You're not going to have it in your bedroom. But for simple things, we don't really need that necessarily. So I just wanted to prove that to you. I'll share the code in the link to the video, in the video description rather. But here's what I thought. I came up with this idea a couple hours ago. So the first thing I did was I said, how do I get data from Google Images? And I found this script which does that. It's just some Python code for getting images, and I think no, this isn't it. I'll share it in a gist. I found it somewhere, and it seems to work. Basically, it works. I'm just gonna delete the images that I have to show you how to use it. So I'm gonna do rmrf train, rmrf valid, and I'll explain those directory structures. This is like for a total noob, right? If you're not following me yet, don't worry about it. So let's get some data. So I'm in my folder. I've got the searcher. This is that script we were just looking at in Sublime. It downloads images from Google, basically. So let me just go in my bash history here far enough to find the command to run the Python script. I'm using Python, and I'll show you the version of all these packages too in just a second. Right, so the first one I'm doing Jeff Bezos. We're doing Python searcher.py. I want 500 images, and I want the label to be Bezos. So let that run. It'll open up Firefox because it's using Selenium WebDriver to do the stuff. I didn't really look at the code, but it worked out of the box with Python 3.5 something. I'm obviously on a Mac, so it's going through. It's requesting more groups of images, and you can see on the left it's moving, and ultimately I think it'll print out some error and then say that it found a bunch of images and it saved them, and that should be good. So I found 600 images downloaded, 600. All right, so what do we have now? I got CD images and I have Bezos. So how many images do we have? 600. So let's just do that again, but we wanted to do it for Gates. So we need pictures of Bill Gates. And I don't know whether or not these are probably copyrighted images. We're not doing anything commercial with them, right? So I don't know. Don't post them somewhere. They're probably somebody else's image. So let's let it get some images of Bill Gates. You can see it's looking for Bill Gates photos. It's doing something there in Firefox. And I used Conda to install Selenium WebDriver. So if you search for Conda Selenium, if you're using Conda, which you probably should, it actually installed relatively quickly. I didn't have to fuss around with a lot. I do have Firefox installed though. So, there could be some dependency there. I don't do a lot of test automation and stuff with Selenium, so I couldn't really tell you. Sometimes it spits out an error, but I don't know what it's doing. Usually it saves a bunch of images. So all right, so it found images. Now notice in images we have all these cryptic, names. So we have 2 directories, 1199 files. That's good. So let's jump into the machine learning component here. And basically, you got to import a bunch of stuff from Keras. Keras is a library that uses TensorFlow or Theano. I'm using TensorFlow. Basically, these are all things you need to do. Image data generator, we'll see what that does. This is basically all the stuff to make the neural network work. I don't know if I'm using this anymore. I might have originally and I thought better, but let's just import this stuff. It says using TensorFlow backend. If you don't have TensorFlow, I would recommend using Conda and do Conda install TensorFlow. If you don't have a GPU or don't know what it is, don't worry about the GPU. It just means that it would use the gaming processor if you have one to do the linear algebra and the matrix math, and it would do it quicker in parallel or something like that. I don't know, but it speeds it up by a hell of a lot. Any serious project, you really wouldn't want that. I have it on another computer, but I'm on my Mac because it's easy to record the screen. So basically all these images that I just downloaded, I don't know if they're all, I don't know what size they are, if the script resized them. I mean, when you're reading somebody else's code, you know, sometimes it looks like gibberish. It looks like he did specify a variable called size, and they are doing some resize operations. So if I had to guess, they were all 256 by 256. Honestly, for a network that's going to be this small with only like 500 images for each label to train on, and the label is like, it's going to be Bezos or it's going to be Gates, so it's like 2 labels, right? So we're going to resize them to 150 by 150, and when I say we, I mean Keras is going to do that automatically. Now, this is the hardest part about machine learning. Getting the images or the data set up in a way that the tools that the really smart people wrote, like this, you know, the underlying code, that this nice clean API, make it work. So we need to do a little massaging here, and we need to create, so train and valid. So I'm going to, hang on, what do we have here? So we have images. So I'm going to say move images to train images. Oops. All right, so now I just basically renamed that. And I'm also going to make a, should I call it TRAIM? All right, so that's spelled right. Now I'm going to create a dir, you know, I'm just going to CP train images to valid images. And you need to copy recursive because you're copying a directory, so put a -r there, I think. So now I need to go into my valid images and cd Bezos and rm anything with a JPEG, because I'm just trying to clean this out. I'm going to move more files in there. So go into Gates and get rid of all the JPEGs. So now I have a little directory structure here. I have my train images, and I have my valid images. Keep in mind, my train images have all the images that I downloaded. Now I need to go into train, and I need to go into Bezos. And there are better ways to do this. I just want to knock this out really fast. And not fuss around with it too much. So I found this bash command that basically will take the I'm in Bezos, I need to put it in the gate. So what it'll do is it'll get the top 50 files from where I'm at. If I do ls head 50, that'll find 50 files and it'll move them per the MV to my valid images. And I'm going to do that for Bezos because I'm in Bezos. Now I'm going to go back into Gates and I'm going to go move those files into Gates because these are pictures of Bill. So let me just back up here and clear. So if I do ls valid images, well, valid Gates, and I count, whoops, space. Now I have 50 in there, right? So I basically I downloaded some data for training, and I needed to keep some data aside to see if the algorithm worked, right? So of the 500 or 600, whatever images I had of each dude, I just moved 50 to a directory that the model's not going to learn on, but when the algorithm appears to be working, it's going to try it out on those images. So back to the code, and I'll paste this Jupyter notebook. I'm not a bash person, but I just found that. Now, here's the model, right? So I'm not going to talk about this a lot, but if you Google, basic convolutional neural networks, one thing is that the guy and the people who made Keras, they changed the API a lot, so lots of stupid little things might break, like the slight naming conventions will change, so you need to Google that. If you're not getting an error about the size of a layer, if it just says like you need an argument or something like that, that's usually easy to fix. The hard things that screw you up in the beginning are input shapes, and usually it's like the first thing, that, and also the thing right before the activation function that helps the prediction. So I'll just explain this really fast. So we're using a sequential model. Keras has a functional API and a sequential API. When you first get started, I would recommend using the sequential API. We're going to add a convolutional layer 2D. And if you want to read about what this API is doing in Jupyter, you can say conv2D, and they have pretty good. So it's going to be filters, kernel size. There are a lot of defaults that just follow what people think are best practices nowadays. But we only have like 1,000 images, right? So to train a network which is structured like the networks that are trying to compete on larger image classification problems like Imagenet would be a little bit stupid. So basically we're taking this, 32 filters, 3 by 3, what the hell do they call that? That's the stride. No, I'm sorry, that's the kernel size. Basically what it does is, say you have an image that's 150 by 150, this will send a 3 by 3 filter over the image, like left to right, up and down, and it'll compute, it'll do a little bit of matrix math against the pixels in that image, and it'll compute something, and that's how it all learns. And the input shape is 150 by 150 by 3. I'm using TensorFlow, so it's like height width or width height and channels. Images, color images that we downloaded have 3 channels, RGB, I think. So that's basically 3. If you're using Theano, it might be 3 by 150 by 150. But if you're dealing with that, you probably had some error. Maybe you had an error already, I don't know. But so basically, all right, so you get a convolutional layer. You pass it through an activation function. The ReLU is sort of like the state-of-the-art thing. Another thing I've found working with non-image data, audio data, is TAN-H, hyperbolic TAN. Works all right sometimes if ReLU appears to be not doing a good job. I can't explain why, but I also want to convey that a lot of people, they don't really know what they're doing. They like to, they read a lot of papers and stuff, and they try to rebuild networks, but at the end of the day, this is an applied video, so we're trying to just get code to work and make some kind of result. So pooling is basically like a dimensionality reduction technique, or almost like a regularization strategy. It prevents overfitting. We're not using we are using some dropout here, but basically you get convolution, you activate, you do some max pooling, you do that again, you add more filters, then you have to flatten it all out and add a dense layer 64. This is somewhat arbitrary. You could try 128. You could try a lot of things. There's no easy way to do like a hyperparameter grid search like there is in scikit-learn and some other packages, because there are a lot of sort of free parameters here. And dropout is basically another strategy to prevent the network from overfitting. And this is key. This is kind of like the number of classes you're trying to predict. Since it's binary, you're going to use a sigmoid. You're going to add a final dense layer of 1. And the loss function is going to be binary cross entropy. If you have, like, let's say you're trying to classify 10 different types of, ships, it would be, dense 10, and I'd be using activation of softmax. And you can read about this. And the loss would be categorical cross entropy. So there are like 2 main cases right here, but we're using binary. Optimizer atom. It's like automated momentum. I don't know. There's a long lineage and history about loss functions and how to optimize it. Like, you hear a lot of people talking about stochastic gradient descent. and peak finding, and basically it's just doing a lot of math, and it's trying to figure out what to change in order to get a better result. And depending on how big a step or small a step and what direction you take, it could take a long time. So Atom is a pretty good general purpose way to do this stuff. And accuracy is just what metric do you want it to report on as it's compiling. So usually I try to, in Jupyter, this is a separate step. I'll hit Shift Enter and execute, and this works. But this is where you'll have to fight errors regarding, like, did I get my shapes right? Am I using the wrong version of the API? And let me see if I'll show you. I'll find the version of Keras after this, because the 1.x is much different from the 2.x. So beware of that. Things are going to drive you crazy. So try to use the new one unless you're copying somebody's code that's written in the old one. And again, there's a sequential API. Sometimes you'll see stuff where it's like X, and it looks like some functional programming stuff, passing around functions as objects and arguments via more parentheses. That's the functional API. All right, so now I'm babbling. So how the hell is it going to get the images? So this is where the magic happens, and that's why I said the most complicated thing you're going to have to do for this is get that Python script to work that I'm going to show you about. And you know what? Yeah, it's in the notes, so you can see it now. Even though I haven't uploaded the video yet, you've already got that. So if that all worked out, image data generator. It's a lot of code going on underneath the scenes, but basically it normalizes the image. It does some shearing, it does some zooming. There are probably at least 7 other options here that image data generator can take. But this is just kind of standard. So we're doing some tweaking to the trained data generator that gives you the option to get more data out of a limited subset of data. So this kind of randomly applies these transformations. We're not going to do anything but rescale the test data. So, we're not doing anything with the test data right now. We're actually just going to do train and validation. So this image data generator, right? So we've got the train generator. It's using this image generator, and it's getting stuff from my train data dir. And my train data dir was defined up here, right? And we did all this horrible, shell commands to get the images moved around. So I had a validation set along with my training data. So basically, image height, image width, we know that's 150 by 150. We're reducing it. How low can you go? Well, you could probably go lower. If the human eye can tell what you're looking at a lower resolution, then the network can probably learn from it. But 150 by 150 is a pretty good starting point. So these are just generators, class mode, binary, and basically, if this works right, it'll say, I need to specify my train data dir. Sorry about that, guys. So if this all works right, it'll show you how many images it found. And it found 1,099 images belonging to 2 classes and 100 images belonging to 2 classes. This refers to my training set, my validation set. So another thing too is, like, if you end up needing to, here's another big thing. So this is nice because you don't need not fit all your stuff in memory, like a bunch of NumPy arrays or something. If you have millions of images, you probably don't want to fit them all into RAM, even if you have like a 64 gigabyte machine or some monster 128 gigabyte machine. I've only got 32, and it does a good job for most things, but that's the nice thing about this. If you could just get your data into these directories, and it could say found 1,000 images belonging to 10 classes, right? It basically just looks to see, in my directory, I said, oh, this is my train images directory. What's in there? It says, oh, Bezos and Gates. There must be 2 labels. So you have to set it up so each folder within your main directory, which is this, is effectively a label. So that was a little confusing at first for me when I started using the library, but it's really, really handy. So try to use it all when you can. And these generators have different properties and methods that can help you get like the labels and the file names and stuff if you need to use that for some comparison, some analysis later. So now you call a model, which you declared up here. You gave it all these properties, this architecture. You compiled it, which basically means is it fucked or not? Sorry, the language. But you will have some foot stomping here. Just keep Googling it. Chances are you screwed up this or you screwed up this. That's my own experience. All right, so basically, model fit generator, you give it a training generator, which we defined here. It's using that image modifier and it's finding stuff in that directory. It's rescaling the image to the size we said, 150 by 150. Batch size, did we define batch size? 16. So batch size just means it's looking at 16 images at a time. Again, it's computationally efficient. So steps per epoch, this is basically saying how many times do you want me to get a batch? So we're doing batches in 16 images per batch, right? So that being said, we are kind of dynamically rotating and shearing the images a little bit. Now for people, I don't know, you don't really see pictures of people sideways. So does that make a whole lot of sense? I don't know. I did a Udacity course about self-driving cars, and when we were doing this traffic sign classification project, maybe since you're looking at signs from different angles, that might be more applicable. But yeah, you know, it's kind of like, think about it, right? Does it make sense to do that? So basically, if I didn't believe there was any point in doing that, I would just say I have 1,099 images, I'm getting 16 at a time. But since we're doing some like random shifting and stuff, I'll let it run more. This will kind of give me more data. And that's the whole point. A lot of times with deep learning, people are even like taking their predictions and them using them as more training data, because the neural networks will do well as you feed it more data. So epochs just means how many times is it going to basically pass through all the data. You know, like every time it, you know, theoretically it should run through all your training data once per epoch. Accuracy should go up per epoch. And it also needs validation data. So we're going to talk about the metrics, right? And these like the validation steps, it's kind of like steps per epoch. I have 100 items, 16 per thing. So basically you run it, right? So you hit go, and I'm on a CPU, right? So it's going to take a little while. But what's happening here, it's going to give you an ETA, and it's going to give you loss and accuracy. And what's happening is that the accuracy is with respect to your training data. This is your training accuracy. It's gonna, once the epoch finishes, it's gonna spit out another metric called validation accuracy. The training accuracy is gonna be from your training data. The validation accuracy is data that the model was not trained on, but you want to see how well the model is generalizing, right? So currently, you know, some other things to think about here too is when you're trying to debug these things or diagnose them, think about like what a random guess would be. So if I just guessed randomly, I would have a 50% chance, right? So if I just said, you know, Bezos, you know, I'd be right 50% of the time. So, you know, from the first epoch, and, you know, we kind of ran through maybe 2,000 images because we were, you know, using these modifiers here, the rescaling, the shear, the zoom, and read up on this. It does a lot of things. Depending on your need, it might make sense to use more. But, you know, my validation accuracy on those 100 images was 62%. So I would say that's definitely better than random. Now, as the epochs keep moving, and we're not going to watch all 30 epochs, this will top out around like 70%, 72, maybe 75%. So, you know, that's pretty good. We just downloaded a bunch of crap from Google via a Python script that we found. And, you know, if you look at the, let me talk about this a little bit. So accuracy is going to keep going up. A lot of times what you'll see is your accuracy will just keep going higher, and your validation accuracy is going to go nowhere sometimes. Like 0.62 to 0.57, that's really just a random change. I wouldn't read into that. You got to let it run for a little while. But you'll see like 0.55, it'll just keep going up. And what's actually happening is the model is overfitting. So it's just learning the features of the specific images really well. And in order to avoid overfitting, usually, get more data or augment your existing data. And I mean, to be honest, like, you can try lots of different network architectures, but if you just keep expanding the number of parameters in the network, it may not really improve anything. Sometimes a simpler network, like a multi-layer perceptron, even for some problems where you're just trying to model a nonlinearity, not necessarily, kind of these invariant features, or, basically what's happening is, like, when you're doing a convolutional network, the filters find attributes anywhere in the image, so it doesn't care about, ignores like the where it found it. So if it thinks Jeff Bezos has a funny nose, or Bill Gates smiles in a weird way or something, it'll be able to detect that anywhere. Now, you're not telling it whether it's supposed to find a nose or a smile or the proportions of the eyes or something like that, but it is finding that. So usually with images, since all these features are kind of space invariant, meaning they could occur anywhere in the image, you need to use convolutions. But when you're just trying to do like some classification for text or some other things that you might normally use scikit-learn for, and just use an SVM or a random forest, I would do a multi-layer perceptron, or if there's any element of sequencing, like text data or sound or something like that, some kind of long short-term memory model, recurrent network. So I think I'm going to stop it there. I'm going to let this run though. I think we're going to get back up to like 60-70%, something like that. It's not overfitting too horribly yet, but it's going to run. I'm going to go get a drink. And in the next video, we're going to say, all right, we've only got like a couple of hundreds of images. It's not a lot of data. Who knows how the resizing procedures really work? Did it distort anything? And what I'm going to do is we're going to use so the convolutions, they learn features and they store them in the model for the most part. So you can use models using weights that are pre-trained, like Imagenet weights, and you can use those weights to predict. So what we're going to do is we're going to use VGG16, which was an older Imagenet contender. I don't know if it won or not, but it's out of some academic group in Europe, and it's relatively easy to run on a CPU. We're going to load it. We're going to include top equals false. I'll explain what that means. And then you can look at the model summary. And we're going to use this model to predict some features. And because we got rid of the last layers, I believe we're going to end up with a 512 dimensional vector for each image. And then we're going to use that 512 dimensional vector to run a multi-layer perceptron to see if that feature, that Imagenet generated, because it's learned about thousands of categories over millions of images, if that is like, better than our 75% scratch Convnet. So hopefully you made it through that. It was kind of long-winded, but I just kind of wanted to do a little bit random. I'll let you know where this ends up to, and it'll be in the notebook, I guess, when I upload it. So, yeah, catch you on the flip side. That didn't work.